Okay, so here we have a uniform thin rod, has a mass 3 kilograms, length of 1.2 meters, right? So let's see here. 1.2 meters is this length. The rotational inertia is given by this formula, and the mass is 3 kilograms. It's free to rotate. We want to find the angular acceleration when it's released from rest. So we want to draw a free body diagram first. So step one, draw the free body diagram of this scenario because we need to calculate all the torques. Right, so we have gravity. Now the gravity doesn't act at the end. The gravity acts at where? The center of mass of the object. And because this is uniform, the center of mass is dead center for this. Now, if this were the only force, then we look at what's touching it. Well, the only thing touching it is the axle, right? So it exerts a normal force. Now, which way is it? Well, this thing's not accelerating to the right or the left, so it's just going to have an upward force, and that's just to hold it in place now. So now we want to figure out what the angular acceleration is, because we're done with the free body diagram. And so we use the net torque equals I alpha. Now, how do we do the torque part? Well, we have to define our axis of rotation. We're going to make it, it's going to rotate around this point. And then we want to define which way is positive. We'll make clockwise the positive direction, counterclockwise the negative direction. Okay, so that's which way it's going to rotate. And then the normal force doesn't exert a torque because the R is 0. And so the only torque we have is from gravity, right? And that distance is 0.6 meters. And it's at a right angle, that R vector, right? So it's 0.6 times mg is equal to the rotational inertia 1/3 ml squared times alpha. M's cancels, it doesn't actually matter what the mass is. And then we can solve for alpha by it's 3 times 0.6 times g over L squared is equal to alpha. So that's 3 times 0.6 times 9.8 divided by what's the overall length, 1.2 squared. Okay, so think about that process, right? That's the important part to understand is we've got to draw that free body diagram. Don't just start plugging in numbers. Because some people, very easy to be like, oh, R times F, I just use this is my R, right? 1.2, that the torque is 1.2 times mg. That's not right, because you got to draw a clear picture about what's happening. Radians per second squared, like that. Okay. Find the tangential acceleration at the rod's center of mass. So that means I want the acceleration right at this point here. Well, that's where we use our kinematics part, where the linear acceleration or tangential acceleration is R times alpha. Now, R is, again, the distance to that point, right? So the R is 0.6 and the alpha is 12.25. So we're going to multiply this by 0.6 and get 7.35 meters per second squared. So interesting to note, look at that center of mass, not quite 9.8, right? And that's because the normal force is helping prevent this thing from falling. If this thing wasn't attached to it, it would just fall at 9.8 meters per second squared. But clearly that normal force slows it down. What's the tangential acceleration over here? Well, for C, still use the same thing, but now the R is different because the distance from the axis of rotation is now 1.2. So kind of interesting, the free end is going to rotate even faster than 9.8 meters per second squared, but that's just the consequence of like how the rotational dynamics works. So for this last part here, we want to determine the angular acceleration when the rod is at the instantation above after it has rotated 30 degrees. Well, let's draw the free body diagram. Gravity acts at the center, and there's still some kind of normal force upward, not necessarily equal. We don't know what it is. But if we set this as our axis of rotation, what's going to be different is when I draw my R vector, look at that. My R, this is 0.6 meters. The R is now not perpendicular to the gravity. Right, so I have to decompose it. We'll use, what color should I use? We'll use blue. I have to decompose this component into a horizontal and vertical component. Right, so this is 0.26 cosine theta. This is 0.6 sine theta. And I only care about the component that's perpendicular to the gravity. Right, don't, easy to mistake to just think like, oh, I'm going to use sine theta because that's the formula. No. We want the component of the R that's perpendicular to the gravity. That's how the torque is calculated. So when we do the net torque here, this guy doesn't exert a torque because the R is 0. We'll say clockwise is positive. This guy exerts a torque of 0.6 cosine, and then they said it's 30 degrees, times mg, because that's what's perpendicular to the gravity, right? So that's 0. And that's equal to, again, I alpha. The I is 1/3 ml squared times alpha. The m's can cancel. I can multiply by 3 and divide by L squared. And what's L? L is still 1.2. And that's going to give you the angular acceleration. So 3 times 0.6 times cosine of 30 degrees divided by 1.2 squared. And now it's 1.08 radians per second squared. So notice that the angular acceleration is definitely different now that we've... oops, I forgot to multiply by 9.8. Sorry. Times 9.8. I left that out. I was going to say 10.6. So the angular acceleration has changed as it's moved down, as it's rotated, which means we can't use kinematic. Just as a side note, we can't use kinematics to solve any of the motion here because the acceleration is not constant. Angular acceleration is clearly varying because the torque actually varies as it swings down.